lecture is going to start in 5 minutes. I request everyone to please be seated. Hello and good morning to everyone here today. Albert Einstein once said, "The important thing is not to stop questioning. Curiosity has its own reason for existing." This quote highlights the value of continuous curiosity and learning. A curious and inquiring mind is crucial for making path-breaking discoveries and advancing fundamental science. We have the privilege of hosting a renowned scientist and personality who has embodied Einstein's words. Thank you for being here with us today, Professor Carl-Henrik Heldin. On behalf of IIT Madras and the Office of Global Engagement and everyone here, I am honored to welcome you today. A very warm welcome to everyone gathered here for the IIT Madras Eminent Speaker Lecture Series. I am Richu George and it is my pleasure to welcome you all to today's lecture. Without further ado, I would like to invite Professor Shanti Pawan, Dean Academic Research, to deliver the welcome address. Over to you, Professor Shanti.
A very warm welcome to all friends, young and old. So it's great to see such a big crowd here at 10 in the morning, at 11 in the morning. So the Eminent Lecture Series has been initiated by IIT Madras in order to attract world-class speakers to the campus and make Chennai a center for intellectual discussion and debate. We are very proud and absolutely delighted to have our very distinguished speaker here today. He's a world-renowned authority on cancer research, and I'm sure all of you will have a lot of questions and very interesting discussions with him. This is also a part of IIT's initiative called Science for All, and the aim is to be able to take science to the public at large and encourage scientific debate and questioning. So with these words, I again have this pleasant job of welcoming all of you to the series. This is the first talk in the series and many more will follow. Thank you very much.
Thank you for sharing your thoughts with us, Professor Shanti. I now invite Professor Manu Santanam, Dean ICSR, to introduce the lecture series.
Good morning to one and all. I join my colleague, Professor Shanti Pawan, in welcoming all of you today to this very important start for IIT Madras, the Eminent Expert Lecture Series. So, Eminent Speaker Lecture Series is a platform created by IIT Madras to host the best brains and minds who are shaping humanity today. It is driven by the motto, Science for All, as Professor Shanti Pawan already mentioned. Through this series, we wish to host the brilliant, the most important and critical thinkers who are improving the society through their immense contributions. By inviting these inspiring individuals to interact with us here, we also want to make Chennai the capital of intellectual thought leadership. And being a prominent institute within Chennai, IIT Madras would like to take this opportunity to lead this initiative. We hope that the dialogue that this lecture initiates will help all of us, the entire student community, the researchers, the scientists, and the aspiring scientists who are amongst us today, as well as, of course, citizens at large. And we are very fortunate to have with us the chair of the board of the Nobel Foundation. I'm sure all the kids who are joining us from schools these days, today, have absolutely no doubt in what the Nobel Foundation stands for. It stands for excellence. And every year, everybody waits with bated breath for the announcement of the Nobel Prizes. And I'm sure that this is something that inspires each and every one of us to try and achieve our best in science and in any field of study that we have undertaken. So we are very fortunate to have Professor Carl-Henrik Heldin from Uppsala University in Sweden. And he's going to talk today about his work on cancer research, which I'm sure is going to be extremely inspiring for all of us. So without further ado, I'll request Richu to take the proceedings further. And thank you all once again for being here this morning. And let's hope it's a very engaging session for all of us. Thank you.
Thank you, Professor Manu. It is my pleasure to introduce the man of the hour, Professor Carl-Henrik Heldin. Professor Heldin is a cancer researcher interested in the elucidation of signaling pathways, regulating cell proliferation, migration, and survival, and how these pathways are perturbed in cancer cells. Professor Heldin's research interest is related to the mechanisms of signal transduction by growth regulatory factors, as well as their normal function and role in disease. Since 1992, he has been a professor in molecular cell biology at the Department of Medical Biochemistry and Microbiology at Uppsala University. Between 1986 and 2017, he was the director of the Uppsala branch of the Ludwig Institute for Cancer Research. He obtained his PhD degree in medical and physiological chemistry in 1980 from the University of Uppsala, where he continued to work until 1985 using a position sponsored by the Swedish Cancer Society. Professor Heldin has published more than 440 research articles and has been cited more than 70,000 times. He has received several scientific awards, including the Prix Antoine Lacasson in 1989, K. Fernstrom's Large Medical Prize in 1993, the Pescola American Association for Cancer Research Award in 2002, and Anders Jahr's Large Medical Prize in 2019. His previous positions include Vice President of the European Research Council, Chair of the European Molecular Biology Organization, and Chair of the Science for Life Laboratory. All his scientific achievements brings him the accolade of being the chairman of the board of the Nobel Foundation. Thank you for being here with us today, Professor Heldin. The stage is yours.
Thank you so much. Too bad I never do slides. Like from there, we can take next. Okay. Something to point? Yes. Pointer actually visibly the screen, so there is one point. Okay. You can just freely walk. Okay. Thank you. Vanakkam. It's a great pleasure to be here, and I will start by thanking the organizers for inviting me to Chennai. I have spent some wonderful days here in Chennai and have learned a lot about the city as well as about the excellent work that is ongoing at IIT. And I'm so impressed about this green and beautiful campus area, which is, I think, unique in the world and very impressive. So what I'd like to do today is to talk a little bit about cancer in general with inspiration from the Nobel Prizes. And I'd like to start to say a few words about the Nobel Prizes. So if I can have the first slide, please. Next slide, please. Thank you. So you know that Alfred Nobel installed the Nobel Prizes. And next slide, please. Thank you. So Alfred Nobel, thank you. Excellent. So Alfred Nobel, never mind. He was born in 1833 in Sweden, and he died the 10th of December, 1896. He spoke 5 languages fluently at the age of 17. He invented dynamite and held 355 patents, so he was a very skillful innovator. He's a chemist, inventor, engineer, entrepreneur, and businessman. And he created an industrial empire of more than 90 companies in 20 different countries. And in the end of his life, he was very rich. In his will, which he wrote in 1895, he stipulated that his fortune should go to prizes to those who shall have conferred the greatest benefit on mankind in the fields of physics, chemistry, physiology or medicine, literature, and peace. And he also identified who should have the responsibilities to select the candidates for these prizes. So in the case of physics, chemistry, there is the Royal Swedish Academy of Sciences, and the prize in economy has been added more recently, 50 years ago. This is not a real Nobel Prize, it's a prize from the Swedish Central Bank in the honor of Alfred Nobel, but it is treated like a Nobel Prize. He also decided that the prize in physiology or medicine should be awarded by the Nobel Assembly at the Karolinska Institute, which is the University of Stockholm. And he decided that the literature prize should be in the hands of the Swedish Academy, and the Peace Prize by the Norwegian Nobel Committee. And you may ask, why did he choose to put the Peace Prize in Norway and the rest of the prizes in Sweden? But at this time, Sweden and Norway was in a union. And maybe he felt that the Norwegian parliament was one of the more progressive ones in Europe, if not in the world at that time, and suitable to have the responsibility for the Peace Prize. So in his will, he says that all his assets, or after he died, all his assets were sold and brought to Sweden. Since he had activities all over the world, his fortune was distributed in many countries, most of it in France. And it was not a trivial thing to collect all this fortune and bring it to Sweden. And the person who did it was actually armed with a gun and during this and transported enormous amounts of money in carriages. It was quite an adventurous task. And the establishing of the prizes was an exciting but difficult process. It was not well received by everyone in Sweden. And for instance, the King of Sweden was against it. He felt that it was not really appropriate to give out so much money to prizes to people outside Sweden. Relatives of the Alfred Nobel didn't like it either, because they would have liked to have the money themselves. And everything was okay. There has been quite a lot of discussions about the interpretation, because in his will, Alfred Nobel wrote that his prizes could go to those who made the most important discovery the preceding year, which is very difficult if you think of how to deal with that in science prizes as well as in peace and literature as well. So I think this has been interpreted that the realization of the value of these discoveries should have been done during the last year. But this is something that is still discussed. In literature, Thank in literature, he wrote that it should go to the most outstanding work in an ideal direction. This has also been a little bit difficult to interpret. What did he really mean? And I think there are still different opinions about that. Physiology or medicine should go to discovery, that's clear. Physics, discovery or invention, and chemistry, discovery or improvement, which is also some open for interpretation. What did he really mean? But maybe the most controversial was his definition of peace: for fraternity between nations, for the abolition or reduction of standing armies, and for the holding and promotion of peace congresses. As you probably have noticed, the Peace Prize is the most political one, and many people really question some of the controversial decisions that has been made. And it comes down to how to interpret what Alfred Nobel really meant with what would qualify to get the Peace Prize. So the Royal Swedish Academy of Sciences, who then have the responsibility for the prizes in physics, chemistry, and economy, consists of 440 Swedish and 175 foreign members, and they award the prizes that I just mentioned. How the work is really done by separate committees for each prize, and they present a proposal to the whole Academy of Sciences that then make the formal decision. And the prize in physiology or medicine is in the hands of the Nobel Assembly at Karolinska Institutet, which consists of 50 members, but the actual work is done by a smaller committee of 7 or 8 persons, who then has to present their suggestion to this bigger assembly that make the decision. And in the case of the Swedish Academy, they have 18 members and they sit there for life, so the average life age is pretty high in this academy. So they have the responsibility for the Nobel Prize in Literature. Again, the smaller committee that actually selects the candidates, and in the end, the whole academy votes and decides who should get the prize. And then we have the Peace Prize, which is decided by a committee of 5, which is appointed by the Norwegian Parliament. The Nobel Foundation was established in 1900 with a board of which I am the chair. Our role is to manage the assets left by Alfred Nobel, to make sure that there is money to hand out Nobel Prizes even in the future. And we guarantee the independence of the Nobel Prize awarding institutions, and we make sure that they have appropriate guidelines for ethical questions like conflict of interest and so forth. And also we safeguard and maintain the intellectual property rights and try to sort of maintain the reputation of the Nobel Prize. So the prizes are handed out by the King of Sweden during a prize award ceremony, which is always held on December 10 in the Stockholm Concert Hall. It's December 10 because this was the day when Alfred Nobel died. And this is how it looks. So on the podium we have the Nobel laureates to the left, in the front line, those who will get the prize this year, and behind them, those who have got prizes previous years and are here to celebrate their peers. And on the right side, me and others from the board of the Nobel Foundation and from the prize awarding committees. And we have the King and the Queen then who are involved in handing out the prizes. And then in the evening there is a big banquet of 1,300 people sitting in the City Hall of Stockholm. And in the middle there is a long honorary table. And in the middle you can see me there next to the Queen of Sweden, wearing a red dress. So officially I'm the host for the whole thing, and that's why I, of course, had to have the most prominent lady in the country as my partner. So this is a very nice dinner. They put a lot of effort into serving food, which is innovative. And there is speeches during the dinner from the Nobel laureates. And there is entertainment too, which is, at least sometimes has a very high class. And it's televised in Sweden the whole evening, and during that, the television also has interview with the prize winners and make reportage from their laboratories and spread a little bit of information about science in general. So this is a nice opportunity, and it's very popular in Sweden to look at. Many people sit and look at us eating the whole evening. And afterwards there is dance on the top floor, and people mingle and enjoy themselves. So how is it then the procedure to select Nobel Prize winners? Well, the autumn before the year in question, the invitations are sent out to individuals all over the world, around 5,000 for each prize, to nominate candidates for the prize. And the deadline is February 1. And then during the spring, the committees, one for each prize, meet several times to go through the nominations very carefully and select a top group, which are then identified by the end of the spring. And during the summer, these candidates are sent out for external opinions amongst experts in the field. And the answers come back then in late August. And then they meet again, the committees, several times, and eventually in early October, the final proposals are made and the decisions are made. And immediately after the decisions, there is a press conference to announce who gets the prize. And the prizes are awarded on Monday, medicine, Tuesday, physics, Wednesday, chemistry, Thursday, literature, Friday, peace, and the coming Monday, economy, according to sort of a rolling schedule. So Encyclopedia Britannica refers to the Nobel Prize as the most prestigious award given for intellectual achievements. And the Nobel Prize has a trademark with good reputation. So in a big survey in different countries, the question was asked, how highly do you think and feel about the brand of various well-known organizations? And as you can see here, UNICEF comes in the top in Sweden, and the Nobel Prize as number 2. But in other countries like the United States, Germany, and India, the Nobel Prize is actually in the top. And here in India, 81% put that in as 6 or 7 in a scale for 1 to 7, which is pleasing for us who are part of the organization. The Nobel Prize was the first international prize, meaning that Alfred Nobel specifically stated in his will that the prize should be awarded to the, it's my express wish that awarding the prize, no consideration be given to the nationality of the candidates, but that the most worthy shall receive the prize, whether he be Scandinavian or not. This was revolutionary at the time, which, as I said, was plagued with nationalism. And the fact that the Nobel Prize from the start was a truly international prize, I think is one of the reasons why it has been so well recognized and still is. As you can see from this map, which is a few years old, there is a dominance of laureates from Europe and North America, but more and more people also come from other parts of the world, as you see here on this map. So, in addition to sort of the international character of the prize, the fact that it was a substantial amount of money was probably also part of the reason why the Nobel Prize has been prestigious from start. So when it was given out the first time in 1901, the sum given out corresponded to 20 years of salary of a professor in Sweden, so that was quite a lot of money. And it roughly the same now, maybe a little bit less if you compare to the adjustments for salary levels. So the Nobel Prize awarding institutions are completely independent, and their century-long work of selecting laureates is performed with the highest level of expertise and thoroughness. I think this is another reason why there is high regard for the Nobel Prizes. Occasionally they make mistakes, that is for sure, but most of the times they get it right. And the scientific prizes are very rarely questioned. People in the field do accept the choices and feel that appropriate decisions have been made. Of course, it's more controversial than with the Peace Prize, which is more political. But I should stress that the awarding institutions are really independent and are not really subject to pressure from government or from any other. And us in the board doesn't have any information about how they discuss that during that work. We only know who will get the prize at the same time as you will. So there is quite a lot of people from India or of Indian origin who has got the Nobel Prize. So if we start with the Nobel Prize in Physics, it was given to Chandrasekhan Venkata Raman in 1930 for his work on the scattering of light and for the discovery of the effect named after him. He was a truly worthy recipient, one of the standing figures, highest standing figures in physics ever. And he's still very well known, and we talk about Raman's spectroscopy today. I understand that he was also instrumental in the establishment of IIT, which was also very nice. In 1983, Subramanian Chandrasekhar got the prize for his studies on the physical processes of importance to the structure and evolution of the stars. There has been one prize in chemistry awarded to a person of Indian origin, to Venki Ramakrishnan, for his studies of the structure and function of the ribosome, which was rather recent in 2009. So he is now the head of the Royal Academy of Sciences in the United Kingdom. There is two prizes in physiology or medicine that has been given to people with origin here in India. One early one, 1902, to Ronald Ross for his work on malaria, by which he has shown how it enters the organism, a very important discovery at that time. And in 1968, Hargobind Khorana got the prize for the interpretation of the genetic code and its function in protein synthesis. Again, this is one of the landmarks in biology and medicine, which gave him the prize, very well deserved one. And there is two persons from India who has received the Nobel Prize in Literature. 1907, Joseph Rudyard Kipling, for the power of observation, originality of imagination, virility of ideas, and a remarkable talent as narrator. And in 1913, Rabindranath Tagore, very well-known poet for his profound, sensitive, fresh, and beautiful verse. And finally, two persons from India has received the Nobel Prize in Peace. Mother Teresa in 1979 for her work to bring help to suffering humanity, and 2014, rather recently, Kailash Satyarthi for the struggle against the suppression of children and for the right of all children to education. A very important prize, which he received together with Malala, who is the youngest person ever to receive the Nobel Prize, by the way. And then we have the Economy Prize in the memory of Alfred Nobel. Again, two people from India has received this. In 1998, Amartya Kumar Sen for his contribution to welfare economy, and very recently, 2019, Abhijit Banjare for the experimental approach to alleviate global poverty.
This voice is not reachable. Can you keep it? Yes, of course. Thank you, sir.
Thank you. Can you hear me better now? Oh, okay, good. So a few other prizes given to persons from outside of India. Albert Einstein is a very prominent scientist that we have all heard about. He got the 1921 Nobel Prize in Physics for his discovery of the law of photoelectric effect. You may be surprised that he got the prize for the photoelectric effect when he is most well known for his theory of relativity. But the fact was that at that time, very soon after the theory was published, which was done in 2015, the general theory, it was so few people in the world who really understood it, so they didn't dare to give it to him because of that, because it might not be correct, they felt. And the fact is that the predictions from this theory of relativity was proven much, much later. And there has been other Nobel Prizes, for instance, for gravitational waves, which is one of the more recent prizes, which is in line with the predictions made by Albert Einstein. Anyway, he got his prize because everyone realized that he was certainly worthy of a prize. And also the photoelectric effect is something very important, so no problem there. Peter Higgs and Francois Angler got the prize in physics 2013 for the prediction of the Higgs particle, which was also a landmark in physics, which was of extreme importance for our understanding of what matter is. And then we had Alexander Fleming, Ernst Chain, and Howard Florey, who got the 1945 Nobel Prize in Physiology or Medicine for their discovery of penicillin. Again, a landmark in medicine, and really something that has changed the life for all of us. And then the prize to Francis Crick, James Watson, and Maurice Wilkins, 1962, for the double helix structure of DNA. This has also been discussed quite a lot. This is truly one of the most important discoveries in biology. And it has then given us information and knowledge about the mechanism for inheritance by copying the DNA strands. But they actually used the data from Rosalind Franklin, another scientist, and it would have been appropriate to include her in their publication, one would think today, which they didn't. And unfortunately, she died, so she wasn't alive in 1962 and could therefore not receive the prize or share the prize, which she certainly would deserve. And more recently, we have then Emmanuelle Charpentier and Jennifer Doudna, who got the Nobel Prize in Chemistry for the discovery of a method to change DNA. This is the CRISPR-Cas technique, which really have revolutionized not only biological and medical research, which is where this method is a very useful tool, but also have enormous potential for treatment of persons with inherited diseases, and also for improvement of plants and animals. Andrei Geim and Konstantin Novoselov got the 2010 Nobel Prize in Physics for their work on graphene. And they were very innovative, and the graphene is from carbon, the kind of carbon you have in ordinary pencils. And starting with a small piece of that and using just Scotch tape, they could sort of, by repeating treatment with the tape, isolate graphene, which is a very sort of one molecule, one atom thick layer of carbon molecules in a specific structure. And this is an extremely useful compound, which is now being developed for applications in many places in the world. And Shinya Yamanaka and John Gurdon got the 2012 Nobel Prize in Medicine for their work on stem cells. Again, one of those discoveries which has profound importance for clinical treatment and is now being adopted or the attempts are made to use this discovery in clinical practice. So almost 1,000 laureates and organizations have received the Nobel Prizes between 1901 and 2022. The prizes in scientific areas and in literature is always given so far to individuals, but the Peace Prize has sometimes been given to organizations as well. So the Nobel Prize Foundation has some outreach events in order to use the big interest in science and literature and peace coming from the Nobel Prizes. So we have a specific daughter company called the Nobel Prize Outreach for this event. So the aim is to reach a global audience via digital and broadcast media and events in Sweden and abroad. And it produces and manages and maintains also the website, nobelprize.org. So there is also a museum in Stockholm where there is informational and research activities, and they produce traveling exhibitions for large audiences around the world. This is beautifully located in the old town of Stockholm, but it's too small really. And we have now plans to make a larger Nobel Center, also in the center of Stockholm, which will make it possible to have a much more elaborate display of Alfred Nobel and the Nobel Prize laureates and their discoveries. There is also a museum in Oslo, the Nobel Peace Center, where they have activities and exhibitions devoted to the Nobel Peace Prize and the work of the Peace Prize laureates. So amongst the outreach events are what we call the Nobel Week Dialogue. This is held the day before the award ceremony on December 9. And in this particular one, 2012, the theme was the genetic revolution and its impact on society. And amongst those who take part here and give presentations or take part in panel discussions are many Nobel laureates that are invited for this purpose. And I had personally the pleasure to take part in one of the events in Goa in India 5 years ago. This was directed again towards teachers in India, and it was a very pleasant experience. And here, Mario Molina, who got the 1995 Nobel Prize in Chemistry, meets with children during the Nobel Week Dialogue in Gothenburg 2013. And much of the activities from the Nobel Foundation is directed against the pupils, against young people, to inspire them to learn about science and important in science and maybe even become scientists themselves. And here is another example. Barry Marshall, who got the Nobel Prize 2005, visited students in Beijing in China. So what are then the challenges that we see with the Nobel Prizes? Well, clearly, to maintain the reputation and prestige of the prize is a very high priority. And here we feel that the prize awarding work is the central task, because unless the prize awarding committees do a proper job, there will be no prestige in the Nobel Prizes. So this is absolutely the core. And they do well, and the people who serve on these committees are very devoted to their tasks. Of course, there are challenges, competition from new prizes, some of them being larger than the Nobel Prize, for instance, the breakthrough prizes. And other actors use the same name because, you know, Nobel is a family name in Sweden, and we cannot protect it. People can arrange Nobel events themselves, and some do, which is a little bit of a problem for us. And there is also legal risk. Sometimes we are sued by people who feel that they should have deserved the Nobel Prize, which seems as a silly thing to do because we are a private organization, and of course no one can tell us what to do and not to do. But particularly in America, the legal system is a little bit difficult, and there are opportunities for people who try to do this, and we have had some experience of that, which has been difficult. We also need to secure the economy and be very careful in how we invest the money. Of course, we need to do that in an ethically appropriate way. We are in the limelight, and people really look on what we are doing, and we need to do this in a very careful way. And the strategy is to guard the core, which is the careful selection of Nobel laureates, and to develop appropriate outreach activities. So, the Nobel Prize, according to Alfred Nobel, should be awarded to those who shall have conferred the greatest benefit to mankind. That is, to those who have contributed to our society, who make a difference, who strive to make the world a better place to live in. This was the vision of Alfred Nobel, and it is our task to try to guard that as much as we can. So, moving on to cancer. So cancer is a serious disease, and about 50% of people get cancer during their lifetime, and about 25 die from it. A little bit more in high-income countries, a little bit less in low-income countries. There is a dramatic increase by incidence by age, and there is a large difference in prognosis between different cancer types. Some cancer types can actually be cured today, whereas others, the prognosis is very poor, including, for instance, glioblastomas in the brain or pancreatic cancer. So the cancer is caused by mutations or epigenetic alterations of specific genes in the DNA. And this involves perturbations in signaling pathways that control cell proliferation, migration, death and maturation, and so forth. So the cancer incidence increase because of the increased lifespan, which I have said. If you adjust for age, the incidence increases for certain cancer types in certain countries, but decreases for other cancer types in specific countries. So there is a variety here, which is depending a little bit on lifestyle. And an increasing number of cancer patients are treated. So this is the positive message here I have today. The risk of dying from a cancer diagnosis is far less today compared to what it was 30, 40 years ago. And since still we cannot promise to cure cancer, but there is at least progress made in that direction. So what causes cancer? Well, chemicals, exogenous ones, for instance, tobacco smoking, which is one of the absolutely largest risks involved in getting cancers, but also endogenous chemicals that are produced in our metabolism and causing, for instance, reactive oxygen species. Radiation, which is also giving DNA damage. This is due to ionizing and UV light. Microorganisms, for instance, hepatitis virus B and C, and papillomavirus, Epstein-Barr virus, and also a bacteria, Helicobacter, in the giving rise to stomach cancer. But there are also hereditary factors. You can get a mutated gene from your parents, and that then increases the susceptibility for cancer during your lifetime. This is rather rare. 10–15% of cancers are due to this. And mutations induced during replication is something which also contributes quite a lot to the incidence in cancer. This is really bad luck. Every time a cell divides, which they have to do in order to build the body and also to repair wounds and so forth, there is a risk that the copy machine is not completely correct, but introduces mutations in genes. And if you have bad luck, then these mutations could predispose for cancer. And that is probably more than half of cancer cases, which is something we cannot do anything about. So cancer is a genetic disease. There are some types that are inherited, and cancer is caused by structural genetic changes and/or changes in the gene expression. And most of known carcinogens are mutagenic, that causes mutations then in DNA. And they affect different types of genes, oncogenes, that when they are activated, increase the risk for cancer, or suppressor genes, which if they are inactivated, increase the risk for cancer. And then we have genes that maintain the genomic integrity, which is, for instance, DNA repair machinery, which we all have in order to keep our DNA healthy. If there are defects in this machinery, then of course we will have more mutations that predisposes for cancer. And then there are also some modifiers that will influence also the risk of getting cancer. So genes are often mutated differently in different tumor types, which is illustrated here. The most mutated gene is called TP53. And as you can see from this chart, it is mutated in almost all tumor types, which are listed on the bottom here, and it might be difficult to read. Whereas other oncogenes or tumor suppressor genes are specific for certain tumor types. Like we have KIT for gastrointestinal stromal tumors, and VHL for renal cell carcinoma, and APC in colorectal cancer. So the mutational pattern for different tumor types differ. If we look on a specific tumor type, lung carcinoma, lung cancer is the #1 cancer killer in the world. It's responsible for millions and millions of deaths. And nowadays, people all over the world have sequenced tumors for different types to identify perturbations of the DNA, mutations in the DNA, and doing so for lung carcinoma specimens give information that 25% has a mutation in the oncogene KRAS, 23% in the EGF receptor, which is a tyrosine kinase receptor. And then there are other kinases also that are mutated in this tumor type, whereas in 36% people didn't find any mutations. And there is still then not really known what were the drivers of the tumor in those cases. But fortunately, for those identified drivers, there are no possibilities of providing personalized treatment. I'll come back to that. So these are the signaling pathways which control motility, proliferation, viability, or cytostasis and differentiation. And they consist of receptors on the cell surface, which then bind growth factors, cytokines, chemokines of different kinds. And then they initiate signaling mechanisms inside the cell, which then leads to the various responses. And you can see that RAS has a prominent place in these signaling pathways, which is the one I mentioned, which is very commonly mutated in lung cancer and also in other cancer types. So perturbations of this machinery, consisting of signal transduction molecules, is the reason why we get cancer. And up in the pink corner there are the suppressor type of molecules that suppresses growth via certain pathways. And if you then perturb that, you will sort of remove the brake for proliferation, and that also can contribute to cancer. So now coming to cancer therapy. Surgery, radiation, chemotherapy has been around for more than 60 years, and they are still used a lot, and they are still the sort of basis for treatment of cancer patients. And there has been a tremendous improvement because physicians have learned how to use these methods better and better for patient treatment. And that's the major reason why we see this decline in death from cancer that I mentioned. But each one of these has problems, and in the case of radiation and chemotherapy, quite severe side effects. So we would like to have more specific ways of treating cancers. So we can then modulate signaling pathways, those that I mentioned. We want to suppress the pathways that stimulates growth, survival, invasion of metastasis, angiogenesis, and telomerasis, which are responsible for the eternal life of cancer cells. But we would like to enhance then signals which suppresses growth and promotes apoptosis, cell death. And in addition, immunotherapy has come in during the recent years and shown a splendid success in the treatment of certain specific cancer types. I come back to that. So if we now want to design a personalized medicine, we can attack each one of the cardinal feature of a cancer cell, which was identified by Hanahan and Meinberg in their review from 2011. And these are sustaining proliferative signals, that is when the growth-promoting signals are overactive. We can, for instance, employ EGF receptor inhibitors to combat that. Evading growth suppressors is also something that the cancer learned to do, and we can then employ cyclin-dependent kinase inhibitors. Avoiding immune destruction, this is linked to immunotherapy. The cancer cell learn how to avoid to be destroyed by the immune system. The immune system controls us and checks and recognizes cancers as not self and therefore kills them. However, the cancer can learn how to avoid this. So if you then treat with immune-activated anti-CTLA or PDLA PD-L1 antibodies, you can avoid this. I mentioned that cancer cells have immortality, which is due to the enzyme that lengthens the ends of chromosomes called telomerases. One can then inhibit that to avoid this. There is also a tumor-promoting effect of chronic inflammation. So one can selectively then provide anti-inflammatory drugs, which will help to treat cancers. There is also invasion and metastasis, which is typical for cancer cells. And you should be aware that 90% of those who die from cancer die from metastasis when the disease spreads in the body. So here we can inhibit certain factors involved in this process, for instance, inhibitors of the MET tyrosine kinase. We have also angiogenesis, which is a cardinal feature of tumors. No solid tumor can grow beyond the size of a millimeter without recruiting blood vessels, because the tumor cells are also in need of nutrients and oxygen, and therefore they are dependent on angiogenesis. And one can inhibit angiogenesis with specific inhibitors for the VEGF. And genomic instability is involved in promoting mutations and thereby promoting tumorigenesis. However, this can also be used for treatment because many tumors have mutations in repair mechanisms of DNA, for instance, BRCA genes. So in that case, one can treat them with inhibitors of a second path that also is involved in the repair of DNA, which is called PARP inhibitors. And therefore, this will then make cancer cells die because even they are in need of some repair capacity, whereas the normal cells who have then normal BRCA molecules will survive these inhibitors. And we have then cell death. Tumor cells do not die when they are supposed to die. We have an intrinsic mechanism for suicide in our cells, which is necessary for us because certain cells need to die if they have acquired properties that are dangerous for us. For instance, mutations which can give rise to cancer, or for that sake, infections by viruses and so forth. And you can then inhibit these resisting mechanisms. And finally, the metabolism of cancer cells differ from the metabolism of normal cells, which has become clear recently. It was actually discovered 100 years ago, but more or less forgotten. But now, recently, this has become very an important area of research. And there are then various inhibitors of specific metabolic pathways that can also be employed in order to treat cancer patients. So, precision therapy in oncology means that tailored or personalized or individualized therapy to give the right patient the right drug at the right time, at the right dose, and stop at the right moment. And in order to make this possible, we need biomarkers in order to predict and in order to monitor response. I mentioned kinases a lot, and there are 55 tyrosine kinase receptors in 19 different families. They are displayed here. More than half of them have been linked to cancer development. The EGF receptor in the most left family is the prototype, and I already mentioned that the EGF receptor is often mutated in lung cancer and also in other cancers. But also many other tyrosine kinase receptors are involved in tumorigenesis, and activation of these kinases drives tumorigenesis in many cases. So this links to a Nobel Prize in Physiology or Medicine 1992, which was given to Ed Fisher and Ed Krebs for their discoveries of reversible protein phosphorylation as a biological regulatory mechanisms. And in 1979, Tony Hunter discovered tyrosine phosphorylation. The most common type of phosphorylation occurs on serine and threonine residues. And kinases of that kind are also sometimes implicated in tumorigenesis, but the tyrosine kinases are overrepresented, and that was discovered by Tony Hunter. So activation of this tyrosine kinase receptor can happen in many different ways. They can involve fusion with other proteins, as is exemplified here in different tumors, and there can be many different partners to the ALK intracellular domain, which causes dimerization and oligomerization of it so that it can activate itself in that way. But it can also involve point mutations, which lead to conformational changes in the kinase domain, making it active, or outside the kinase domain as well. That also can promote activation of the kinase. And it can also be overexpressed, not mutated, but by epigenetic mechanisms then seen in too high quantities, and therefore making cells susceptible to stimulation with this particular oncogene. So I mentioned tyrosine kinases as being very important. These are called receptor tyrosine kinases, or RTK. They are often mutated or overexpressed in cancer, as I said. And we have already clinically used a number of tyrosine kinase inhibitors against individual members of this receptor class. But then later on, these RTKs activate RAS. RAS is often mutated in many cases, particularly KRAS. And then downstream of RAS, we have MAP kinases, for instance, BRAF, that is also mutated in certain tumors, melanoma in particular. And here we have also specific low molecular weight kinase inhibitors. And downstream here we have MEK. Again, we have available several low molecular weight inhibitors. Then this leads to activation of ERK, 1 or 2, which then causes phosphorylation of various substrates, which drives proliferation or differentiation. So to make inhibitors for kinases has been straightforward, and I'll come back to that. To inhibit RAS, much more difficult. This is not in itself a kinase, and therefore it's more complicated to target it. But this has been successful very recently. But in this case, one needs to attack each one of the different types of mutations. So glycine number 12 in KRAS is often mutated, but it can be mutated to any other amino acid. And you have to make specific drug for each one of those. So if it is mutated to aspartic acid, or D, then you have this molecule MRTX1133 that actually do work. And there has also been recently reported another one for the mutation in which glycine 12 has been mutated to cysteine. Then another drug works. So this is really a breakthrough, since these mutations are so common in cancer. But it's more difficult than the straightforward kinase inhibitors. This is a kinase. It consists of an N-terminal lobe and a C-terminal lobe. And in between, ATP binds. And ATP is needed by kinases in order to deliver the last phosphate group to a protein. And the protein docks here, and then the phosphate is transferred. So this ATP binding pocket is where low molecular weight inhibitors are sought, and they look a little bit different in different kinases. So it is possible to get specific kinase inhibitors for individual kinases. And this shows a tree of all 500 kinases that we have in our cells. And they are more or less related to each other, depending on how they map amongst these branches. And this upper left one is the tyrosine kinases that often are involved in tumorigenesis. And on my next slide shows a little bit of the kinase inhibitors that has been developed. The red dot here indicates that the inhibitor in question inhibits this particular kinase in the tree. And the size of it refers to the potency. As you can see, some of the inhibitors use imatinib, for instance, up in the right corner is fairly specific, and it inhibits only a few kinases, which makes it rather well tolerated and not giving rise to too many side effects. Whereas other molecules that also are used clinically, like SU11245, inhibits many kinases, which one would think would be useless if you want to treat patients, but it actually works. It gives more side effects, but it is also more efficient in treatment of certain tumors. So now we have a number, more than 40 actually, of tyrosine kinase inhibitors used clinically for the treatment of various cancers. So how can inhibition of a signaling pathway controlling cell growth cause death of cancer cells? If you inhibit a cell to grow, it doesn't necessarily mean that it will die. Normal cell would not die just because you inhibit its proliferation. But tumor cells become addicted to the overactive signaling pathway. And if you then inhibit that, they will actually undergo apoptosis or suicide. And it is also so that the best treatment effect is by inhibition of pathways that drive tumorigenesis. You really have to find the key driver of the particular tumor. And there has been some spectacular breakthroughs in cancer treatment by use of kinase inhibitors. Imatinib that I mentioned, called Gleevec, when is sold, it can be used to treat chronic myeloid leukemia, or CML, because it contains a fusion protein between BCR and the tyrosine kinase abelson. And it can also be used to treat gastrointestinal stromal tumors because KIT is also one of the tyrosine kinase receptors are also inhibited by the same molecule. This, when it was introduced some 20 years ago, was a remarkable success. Patients with these diseases were treated. The tumors disappeared, which caused a lot of excitement and a lot of enthusiasm to develop tyrosine kinase inhibitors also for other kinases. Erlotinib is then developed for lung cancer because it inhibits the EGF receptor with success in some cases, actually in those cases in which the EGF receptor is mutated, and that's a substantial proportion in lung cancer. But it has no effect if there is no mutation in the EGF receptor. And then we have Celaboraf used for treatment of melanoma because it inhibits BRAF. And this is, again, a spectacular treatment effect. However, after a few months, resistance mechanisms appear and the tumor comes back. And this is now the biggest challenge in tumor treatment. And what is happening? Well, there could be activation mutations in the kinase so that it no longer now is inhibited by a specific low molecular weight inhibitor because the ATP binding pocket has been changed in structure. It can be amplified, meaning that there is not much more of the kinase and therefore difficult to inhibit. It can also be activation of alternative signaling pathways that take over and perform the same type of signaling in the absence of a specific receptor. And there can be activation of membrane transporters that pump out the drug so that it's difficult to get enough concentration of the drug intracellularly. So the big challenge now is to try to see how one can avoid the resistance mechanism and sort of preserve the positive treatment effect that I just described. One problem in treatment is also genetic heterogeneity. So it's not, it's of course obvious that different tumor types differ from each other. And I've already told you that the mutational patterns differ quite a lot between different tumor types. But also within a specific tumor, breast tumor for instance, there are varieties of the tumor depending on which cell the tumor arises from. But also within a specific tumor there is differences. So there could be different subclones that are different from each other. And one subclone may respond to treatment whereas another do not. And there is also plasticity so that tumor cells can adopt different phenotypes. This is a challenge. And linked to this is the presence of cancer stem cells. As you know, our normal tissues contain stem cells. We can be differentiated to specific cells that then perform different functions in the body, muscle cells, brain cells, and so forth. In the development of malignancies, in the pre-malignant lesions also the sort of presence of these stem-like cells, and also in the malignant cells, there are a subpopulation, maybe 1% of the cancer cells that are these stem-like properties, which then give rise to the mature tumor, which then is sort of what is treated. But what is working on the majority of the tumor cells may not work on the stem cells, which may be one of the reasons why tumors come back. So to treat cells and also attack the stem cells will be very important. And the stem links to what we refer to epithelial mesenchymal transition, which makes the epithelial tumors undergo a change so they become more like fibroblasts, more mesenchymal, which is illustrated on this slide. And when they do so, they become more invasive. They invade their environment, they enter bloodstreams or lymph vessels, and they are taken by circulation to another place in the body where they form metastasis. And this EMT is needed for this process to be efficient. And when the cells reaches the metastasis site, they revert back to epithelial character by mesenchymal to epithelial transition. So this is a process which has attracted a lot of interest in our group as well as in many others. And we try to understand, first of all, the mechanism behind it, and secondly, whether it can be targeted in tumor treatment, which may be not so easy. I would like to stress that in a solid tumor, there is not only malignant cells, which are the brown cells up to the left here, but there is a number of other normal cell types as well. Cancer-associated fibroblasts in the top, they are sort of developing in the tumor from resident fibroblasts that perform normal functions, provide matrix molecules, for instance. But when they are in the tumor context, they change properties. They start to make a lot of cytokines and growth factors, which stimulates the tumor cells and also helps for the tumor to grow. We have pericytes around blood vessels, and we have endothelial cells that make up the blood vessels. They are also constituents of tumors, and also a possibility to target, because if you starve the cells from blood supply, they might undergo apoptosis. But we have also immune cells of various kinds, myeloid cells as well as lymphocytes, that are trying to attack the tumor cells and kill the tumor cells for us. But unfortunately, the tumor cells has learned techniques to avoid immune attack, which I will come back to. So what are then the strategies here? Well, one can target the cancer cells directly, attack the enemy directly. So that's sort of the most common and obvious way to treat cancer. But one can also attack blood vessels and stroma, so blocking the support that the tumor cells get. So this is now also done clinically, and in particular there are inhibitors of angiogenesis, blood vessel formation, that are often used together with the compounds that attack the cancer cells with some help. And then we have the immune defense, empower the resistance, which is what I have mentioned many times already, has been very successful the recent years. And of course, in order to have an efficient effect, probably one need to combine with different types of treatments. So what are then the targets for cancer therapy? This is a schematic illustration of what I just said. We have all these tyrosine kinase receptors that initiate the intracellular pathways that are driving cell proliferation and migration. And then we have also other receptors that are responsible for apoptosis. And we have the metabolism that are possible to target in order to treat cancers. But then in addition, we can target angiogenesis, targeting the receptors for VEGF, PGF, and FGF. And we can also then empower the immune system by removing the inhibitory effects by the expression of specific receptors at the cancer cell surface, PD-L1, because there are PD-1 molecules on the T cells that recognizes this molecule, and when that happens, the T cell is inhibited. Its capacity goes down. So the immunotherapy then involves using antibodies that can block these inhibitory interactions, either against CTLA-4 or against PD-1 or PD-L1. And this is done now clinically with a lot of promising results for certain tumor types, not for all. And within the specific tumor types, only a fraction of patients are actually cured. This relates to a Nobel Prize that was given to Jim Allison and Tatsuko Honju in 2018 for their discovery of cancer therapy by inhibition of negative immune regulation. And a very important finding. And interestingly, if one treats with these antibodies, you see that there's only a sub-fraction of patients responding, but some of them are really treated. Tumor doesn't come back. If you compare to targeted therapy using kinase inhibitors or other antibodies or smaller molecules that directly target the tumor cell, you see that if you choose the right treatment, patients will respond, but eventually resistance mechanism kicks in and the tumor comes back. So what we really need to do is to find ways of combining various treatments using then inhibitors of the immunotherapy that I mentioned, together with radiotherapy, chemotherapy, or tyrosine kinase inhibitors. And by doing so, the hope is that we will sort of lift the curve so that a larger proportion of patients are actually cured. I mentioned just finally here that there is also attempts to use a method called CAR, which means that you take T cells from the patients and then you transfect them with an artificial molecule, which combines the effector parts of the components of the T cell receptor and makes it extremely efficient in activating T cells. So you can, by inserting this molecule, make the T cells extremely efficient and aggressive and killing the cancer cells. And that works, but this procedure is very expensive. So what are then the emerging paradigm shifts? Well, we need individualized treatment based on tumor and patient profiling. And we need better tumor markers for early detection and monitoring of treatment. And this early detection is very much dependent on improved imaging techniques. And we need identification of the Achilles heels of tumors, that we need to identify the drivers of the tumor. And we need reprogramming. One could possibly think of reprogramming of tumor cells, making them less aggressive, which works with certain very specific type of tumors. One can also think of improved methods to target tumor metabolism, angiogenesis, and tumor stroma, which is then sort of not attacking the cancer cells directly, but attacking the normal cells around the tumor cells. And we need improved immunotherapy, as I have mentioned, and we need to optimize the combination of treatments. And I think this goes without saying that combination of different treatments will be necessary to have a lasting therapy effect and avoid resistance mechanisms. André.
Thank you, Professor Heldin, for this wonderful and really informative and insights into the Nobel Foundation and the Nobel Prize. And it's really inspiring to see your work on cancer, and we're really thankful for all that you do for the community. We have some time for a few questions. I think we can take about 5 or 6 questions. So please raise your hand and wait for the microphone.
Hello. Sir, I am Akhtar. Sir, so my question is not technical question. I want to ask.
It's not on. Closer to your mouth.
Okay. So, thinking from government's view. Hello. Okay. So, thinking from government's view, for a country like India having more population, so the money should be spent more on cancer research or creating cancer awareness?
The question is whether we should spend more money on cancer research. Well, I am a cancer researcher myself, and I think that is a good idea. But of course, we all need to address many other important diseases as well, and also many other sectors of science. So we need to cover the whole field, I would think.
And in what way is government of all countries, like all countries are lacking creating the awareness, because still the cases keep on increasing?
I could not catch that, sorry.
Like, what all steps should other countries, including Indian government should take that they are not taking right now, creating awareness of cancer, because still the cancer cases are rising day by day.
It's a little bit difficult to hear. Can someone repeat the
This
question?
question is, what should India and other countries do other than what we're already doing in terms of cancer awareness?
What should other countries do?
Yeah, and India.
Well, in order to minimize cancer cases and cancer death, the absolutely most important thing to do is preventive. It's a matter of lifestyle. Not smoke is number one. That is certainly, if people didn't smoke, we would decrease the number of cancer deaths by a third maybe, which is an enormous figure. It has to do with alcohol consumption, with how we eat. We should avoid certain types of food. In India, I think you eat pretty healthy food, but in other countries, the consumption of beef and fried meat is too high. And we also need to be careful with sun, particularly in countries where we are not used to sun, like in my own country, where people go on holiday in sunny countries and expose themselves. And UV light is causing mutations in the skin, so that's dangerous. We should be careful with that. But as I said, many people who get cancer, they simply have had bad luck. So one cannot say that it was due to that they didn't live had an appropriate lifestyle. Some people simply have bad luck. But we can minimize the risk at least a little bit by living healthy. So what should we do then in order to not only avoid things, but do things that actively prevents? Well, exercise. So keeping good physical shape helps against cancer as well as many other severe diseases. So that's a good thing.
Check it. I have the mic to your right. The next question. Thank you, doctor. Can you hear me? Yes. So I have a question for you as the chairman of the board of the Nobel Foundation. You mentioned in your presentation about how Albert Einstein got his Nobel Prize eventually for the photoelectric effect and not for his general theory of relativity. The reason you ascribed was that nobody understood at that point what his theory was all about. So my question is, how much, and we now know that the Nobel Prize has such reputation and honor, that every researcher, every aspiring doctor wants to find out the area of research which would allow him to get a Nobel Prize at some point of time. So how much is the Nobel Prize an inhibitor of groundbreaking research? Because we can see researchers choosing only topics which are incremental discoveries, small incremental improvements in the field of study, rather than totally groundbreaking effort which would completely change the face of understanding what cancer is, for instance, or any other field of study. So how much is Nobel Prize itself an inhibitor of groundbreaking research?
So I couldn't catch all of that question. Could you give me the essence?
If I understood right, he's asking
I'll just try to explain his question where he said that, like, when you gave an example of Albert Einstein, that he could not get the prize for relativity, but photoelectric effect. So what do you believe as a chair of the Nobel Foundation, it did act as an inhibitor of getting a Nobel Prize for somebody where it was truly deserved? That's what your question was, I believe, right?
I still didn't get it.
Foundation's ability to understand path-breaking science.
Yeah. Well, this is the key question, really. How is it possible to identify the most deserving Nobel Prize laureates? And of course, this has to involve a very careful analysis of the nominations that comes in, and also make sure that you get nominations so that all possible candidates are in the discussion. It is, of course, very difficult to know what is a real breakthrough immediately. So that's why there is often a delay between when a discovery has been made and when people got the prize. And this delay can sometimes be very long. But I think that is one of the reasons why the Nobel committees are taking their time in order to really understand what was a real breakthrough, and then they award it when they are sure. And of course, there is also a stiff competition and difficult to compare prices in a certain sub-area with another sub-area, and to some extent it becomes a little bit a matter of taste, whether you think that one thing is more important than the other. But I think that overall, the prize awarding committees have been very successful in finding deserving candidates. But that doesn't mean that there are not a number of other possible candidates that would be equally deserving, if that answers your question.
No, not exactly, but it's fine.
My name is Ravi Shankar Chandu. I am the President Society for Engineering Education India, a not-for-profit society. And as Einstein's case, not understanding relativity is not problem of Einstein, but the people who gave Nobel Prize in that year. So that sort of issues in the committee of selection of Nobel Prizes might have happened till now, starting from 1900, from where these Nobel Prizes were instituted. As he told, the Swedish king was opposing these prizes. But today, if you go to your king and ask him, shall we stop this? He will say no. So there is a change of opinion. That opinion was time dependent. Coming to Indians, the person who invented boson was not given prize, but a person who collected how to collect bosons in a particular area is given Nobel Prize. So would you like to amend those, instances where Bose was not given the Nobel Prize, which he really deserves? And quite often I read in the science essays in India that there are 5-6 Indian academicians who really deserve Nobel Prize, but people who used their concepts, they are getting Nobel Prizes. This sort of, whatever we call injustice or oversight or whatever we call, probably would you like to make amends now and give Nobel Prize for Bose? That is one issue.
Sir, if you can make the question short, we can take on a few more questions from the audience. So.
Yeah, just one more, this one. What I observe is, in UK, anytime, there will be 100 Nobel Prize winners living. And most of the Indian Nobel Prizes have to leave India to get Nobel Prize. That's what the recent history has shown us. So tell us how to get a Nobel Prize and give some of our peers at IITM.
Let me start with the first part of your question. So the Nobel Prize awarding committees really try to go back to the origin, to try to identify the person who have done the breakthroughs, who were first with the original thought, not necessarily the same people that dominated the field thereafter. Sometimes the choices have been criticized, and almost always it's a matter of finding a fourth person, or people feel that a fourth person should be included amongst the three who got the prize, because this person has also contributed to the discovery. But there is a limit of 3, which makes it difficult for the Nobel Prize awarding institutions to be completely fair all the time. So that might be one of the reasons that is behind what you're mentioning. And the second question was related to, I forgot your second question. You had a second question.
His second question was if there's been any decisions that you think was not right, and then if you would like to change.
There have been mistakes for sure, and the prize has been given, the chemistry prize, to DTT because it was shown to be very efficient to address the malaria problem. Now we know that DTT is a horrible substance that causes a lot of problems, and today you wouldn't really get a prize for that. There was also a prize for lobotomy in the end of the 40s, which was seen as a big improvement in psychiatry. Now we know that this is a horrible treatment of patients, which is not ethical. So that was a mistake, clearly. And I think it is linking to what I said, that the prize committees often wait some time before they award the prize in order to be sure that what they award is a true discovery, worthy of the Nobel Prize, and not something which seemed to be very important at the time, but then after a while it was not a good idea.
Hello, sir. I'm over to your left. Yeah. So I'm Nandana, and firstly, I want to thank you for your time and for giving an amazing talk. And so my question for you is, what do you think about the underrepresentation of the women in the Nobel Prize? Because as of 2022, we have 60 women who won the Nobel Prize approximately, and closely 900 men.
Yeah.
So why do you think there's a disparity in the percentage?
Yeah, that's an excellent question. And it is certainly something we are very much aware of. The Nobel Prize awarding committees, they don't have any quotas, so they try to select what they feel is the most worthy recipients. It has happened so that very few women has got the prize, which is unfortunate. One reason, at least for the scientific prizes, is that there were at 20, 30, 40, 50 years ago, not so many women involved in physics, chemistry, for instance, even medicine. Now there is much more, and the number of prominent female scientists increases very rapidly. So my expectation is that in the future there will be much more women amongst the Nobel laureates. But I fully agree with you that it doesn't look good that we today have so few women as Nobel laureates.
Yes, sir. The thing is, even 50, 60 years ago, there's something called the Matilda effect that I recently read about, which is the bias against acknowledging the achievements of women scientists whose work is pushed to the footnotes and attributed to their male colleagues. So there have been so many women who have been affected by this, for example, Martha Gautier, Jocelyn Bell Warner, and these women, their achievements did not go unnoticed because they did some huge things that today we should be really thankful for, like the discovery of nuclear fission, discovery of the DNA structure, the discovery of radio pulsars. But obviously their discoveries were recognized, but their longtime male colleagues and their male counterparts were awarded the Nobel Prize Award, and they weren't given the credit that they deserve for it. So why do you think that is?
No, you're absolutely right. There was a serious omission of Meitner in the physics prize that you referred to. She should have been amongst the recipients, definitely. So that was a clear mistake by the Nobel Prize Committee at that time. I hope that kind of mistakes are not happening now, and I'm not aware of any omissions of that kind for the recent years.
Hello, sir. Thank you for this wonderful talk. At the left of me. Yes. We talked about the chemical aspect of the cancer, but as we know, human body is a complex entity, complex system, both mechanical as well as electrical, as well as these chemical aspects of cancer should not be avoided. As far as I'm seeing that the mechanical electrical aspects of this cancer are ignored in this chemical aspect. Is it possible to treat human body as a mechanically and treat cancer mechanically only, ignoring the chemical aspect? Because a lot of research has been done on the chemical aspect, but there has been a lot to do in the mechanical aspect, like the shear stress and all.
Can you help me? Can you help me?
Can the questions can be crisp and sharp? And one question per person.
I'm sorry, I couldn't catch the
Talk to you after the talk. We can talk to
Okay. I'm sorry, I couldn't hear what you said.
I think we can
Come
take
up to
on
me
one
after
more
the
question from the audience, and then we'll move on.
It's on.
Recent study states that synthetic detergents and the chemical which can make fruits ripe may cause 4 types of cancers. What can a normal man do to prevent himself from cancer?
What can a normal man do to prevent himself from cancer as a gist of it?
What can?
What can a regular person do to prevent cancer?
That's a very good question. So it's a matter of lifestyle. We should not smoke. We should eat proper food, avoid fried meat in particular, beef, which I know that you're avoiding, so that's good. And we should be careful not to expose ourselves to much sunshine or radiation of any other kind. So that is what we can do. And we can also keep a healthy lifestyle by exercising and being outdoor and being involved in that kind of activities. That doesn't completely minimize the risk to get cancer, but at least it reduces the risk.
Respected sir, I was student from respected sir, I am a student from Kendra Vidyalaya IIT Chennai, and I had a small question about cancer. So, according to your presentation, which was very amazing, you suggested many ways of avoiding cancer. But would there be a way to control cancer and rather than try a way to destroy it? Like for instance, the tumor cells in our like if we were to have cancer, there would be a tumor in our body. Would it be possible to control the tumor rather than try to destroy it?
Would it be possible to control cancer by? Yes. This is a very good question too. Some cancers are very common, for instance, prostate cancer amongst men. But 19 out of 20 who get the cancer diagnosis in prostate of us men will die from something else. So, and to treat prostate cancer is difficult and have severe side effects. So it would be important not to treat the 19 that will not die from this disease anyway, but rather find ways of carefully watching and waiting and monitoring the progress of the disease. And if the disease then starts to grow, maybe one can find ways of inhibiting it without removing the tumor, but rather keeping it under control with rather low side effects, which would sort of be beneficial for the patients. So this is certainly something to think of. Although most cancers are of the type when one cannot guarantee that the patient will survive, and then the doctors put in whatever they have, being very aggressive in the treatment.
We'll take the last question now.
Good afternoon, Professor. Can you hear me? According to your recent publication of 2020, you specified about PDGFR beta kinases that can be suppressed by kinase NAPP1 that are used for the treatment of breast cancer. But this type of breast cancer actually causes tumor. There are certain types of cancer that don't cause tumors, like leukemia and blood cancer, that can't be targeted to a specific site as blood flows throughout our body. In that case, would you say that immunotherapy is better for cancer that we can't specify, or we could use specific targeting such as NAPP1?
This was a very insightful question, but I didn't understand all of it. Yeah. 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 Well, immunotherapy, I think, has the future. So this is a very important part of future cancer treatment, I'm sure, because it sort of empowers our own defense mechanism to find and kill the cancer, which also in theory means that you can treat cancer that has spread for metastasis, which is very difficult with conventional techniques. So yes, I think that immunotherapy is very important. Did that answer your question? Okay.
Okay. Considering we have a lot more people who want to ask questions, we'll just take 2 more.
Hello, sir. Hello, sir. In solid tumors, will circulating tumor cells be an effective option for diagnosis and treatment, and will it take the place of biopsies that we do now? In solid tumors,
yes.
When circulating tumor cells, am I audible?
Yeah, we can hear you.
Yeah, so will circulating tumor cells be an effective option for diagnosis and treatment in solid tumors? And can it take the place of biopsies that we do now as a standard of care?
Right. Well, the basis for treatment of solid tumors is to take a biopsy and look at the tumor cells, and also stain for various markers, as well as sequence the DNA to see which genes are mutated, and based on that kind of information, select the most appropriate treatment.
My question was, will circulating tumor cells be taking the place of biopsies for diagnosis or treatment?
Yeah. But this is also a very insightful question. Tumors, solid tumors, they are sometimes leaving the primary tumor out into the circulation and can be found in ordinary blood samples. And if you can identify them there, you can study them in order to try to find the appropriate characteristics which will guide your therapy. This is something which is being explored, and there is a lot of hopes that this will work, but it is difficult, and so far this has not become clinical routine.
Hello, sir.
Good afternoon, sir. To your right. Good afternoon, sir. I really enjoyed your talk, so I thank you for that. My question is simple. What I wanted to ask was, we do agree that prevention is better than cure, but still, there are many mutable types of cancer. So some of them are asymptomatic, which do not have symptoms. So how do we detect these? And we have many instances where people lead healthy lifestyles but still get cancer. So how do we detect cancer in such cases?
There are asymptomatic types of cancers. So how do you detect cancer in such cases even if people live like a really healthy lifestyle?
How do one detect cancer? Well, the detection of, thank you. The detection of cancer is crucial, and the earlier you detect it, the better chance to treat it. So the question then is, how do you detect cancers early enough? But there are certain screening programs, for instance, for breast cancer with mammography, and other cancer types, prostate cancer with PCA, that can be done to monitor the development of the cancer. And I emphasized during my talk that imaging techniques of various kinds, when you see through the body and try to find the tumor cells using specific probes that will bind to the tumor cells and make it possible to see it, will become very important in the future. So it's a combination of different techniques involved. But what we really need is biomarkers, preferably those in blood, which is easy to get from patients without much problems. And if we can, in the blood, see markers for various tumors, preferentially at a very early stage, that would mean a lot for us to detect cancer early enough to treat the patients.
Hello. Last question from there.
Hello, sir. My question is, your work mostly they have been done on the biochemical aspects like the kinases and all this, but there are also other factors like pressure, temperature gradients, and also fluid shear stress that are there present in our body. So do they also influence on the biochemical factors for the production of some kinases, certain kinases?
So, what? Right. So in the end, everything is biochemistry. But I'm not sure if I quote your question correctly, if stress and psychology can also be involved?
Actually, mechanical stresses like fluid shear stress, and mostly in ovarian cancer, they actually metastasize to the peritoneum fluid.
Well, that I don't know, but chronic inflammation, if you have some chronic inflammation in your body, that predisposes for tumor formation. So that is a risk factor. Was that your question? Or?
No, sir. My question was the mechanical factor. Do they influence the chemical factors?
The mechanical factors. I see. Well, indirectly it could, because if the stroma around tumors are dense, that it has very much collagen fibers, that is a risk factor, for instance, in breast cancer. And that links to the mechanical aspects of the tissue, which, for instance, makes it more easy to activate TGF-beta and other cytocancer growth factors. So there are mechanical factors involved in certain tumor types, yes.
Thank you to all of the people who asked the questions. They have a lot more questions, but we have to wind up. Thank you. Thanks a lot, Professor Heldin, for answering all the questions so patiently. You can be seated now.
Please feel free to come up to me and ask specific questions if you have more. I'll be here.
Thank you,
Thank you
Professor
so much.
Heldin. Thank you. I request Professor Sachin Gunde, Advisor to Office of Global Engagement, to deliver the vote of thanks. Professor, you can be seated.
Excuse me?
You can be seated here.
Okay. Thank you.
Good afternoon, everyone. And I know that now, since our minds are filled with the knowledge, everybody probably looking forward to fill our stomach with food, right? Yes or no? Yes, right? So I'll make sure that I take not more than 45 minutes to express my vote of thanks. So please bear with me. Well, not really. I'll just try to probably finish it as soon as possible. Thank you, Professor Heldin, for being here. Right? I believe that to start with, he really deserves a standing ovation for one fact, at least, that at this age he was on the stage for at least 1 hour and 40 minutes, answering the questions and giving the talk. So thank you very much. And it was really a pleasure to have you here. Thank you. I would like to first start my 45 minutes of vote of thanks, thanking the IIT administration, the director, Professor Kamakoti, the deans, particularly the Dean of Global Engagement, Professor Raghu Rengasamy, then Professor Mahesh Panchagnula, the Dean of Alumni and Corporate Relations, the Office of the Global Engagement staff, the Office of the ACR, the staff there, then the most important mention I would like to have that we had a formal committee who had worked very hard over the last 6 months to have Professor Carl here, which comprises of Professor Rahul Marathe, then we have Dr. Anindita Sahu, Professor Nilesh Upadhyay, and Dr. Chandra, those who could not make it here. I would also like to thank the registrar and the IIT support staff, the transportation cell. I would like to thank the principal of the various schools, including the principal of our Kendriya Vidyalaya at IIT Madras, for sparing time and sending the kids here to get some inspiration from it. I would like to thank everybody, those who are involved and then made it all the way to here. Like, thank you, the people from consulate and everything. And then one more time, I take this opportunity to thank Professor Carl being here amongst us for delivering wonderful talk. We'll probably still have around like 10 to 15 minutes of interaction since he said that, right? So please feel free to not to really kind of do him, but then interact with him for next 10 to 15 minutes. Once again, thank you everyone for being here. And then above all, as I said, thanks to every one of you, which on a working day, on Tuesday, and then in the morning session, everybody came in here. One of the things which I was told when we scheduled this talk was that maybe we made a mistake that having scheduled this talk on a working day in the morning session, and then we booked such a big hall, and then that made me worry a little bit, right? But now I understand that I need not have to worry because of Professor Carl's credibility and in his outreach as far as the topic is concerned. So thank you everyone for being here, and then we probably look forward for another interesting talk in future. Thank you very much.
Thank you, Professor Sachin. This brings us to the end of today's lecture. I would like to thank Professor Heldin. Thank you, Professor Heldin, for sharing your knowledge and insights with us today. I hope everyone here found the lecture informative and inspiring. Clearly, all found it quite amusing as well. A heartfelt thank you to everyone who joined us today. Thank you and good day.